Hi everyone, the next topic is tree-based methods. The tree-based method is a framework for regression and classification by simple split of variables. So it can deal with regression and classification problems, but it introduces a new idea on simple linear regression models. So think about the regression problem to regress salary of baseball players on years of experience and the number of hits generated in the previous year. So in linear regression, we determine the coefficient of years and hits. Instead, tree-based methods use splits. What's the most important split between players with lower salary and higher salary? Then most important criterion is whether or not years is less than 4.5. So if the years of experience is less than 4.5, salary is on average 5.11. If the years of experience is more than 4.5, we have another split, hits. And hits, the number of hits is less than 117 or equal. Average salary is 6.00. If the number of hits is more than 117, average salary is 6.74. So in this way, the tree-based methods use important splits to determine the fitted value. So this is the illustrative explanation of the previous example, this example. So at first, okay, so these points, each point corresponds to baseball player. So each baseball player has some salary, for example, 6.8. And x1 is years and x2 is hits. Most important splits is whether or not years is more than 4.5. So players on the left-hand side of this line has lower salary, while right-hand side has higher salary in this case. Then next important split is this. So this side we have higher salary and this side we have lower salary. And each split is made so that the sum of squared errors is minimized. So this first line minimizes the sum of squared errors if we are allowed to use only one value for this side and this side. So this is another illustrative example of tree-based methods. How many splits in this graph? We have actually 4 splits. The first split is probably here, second split is here, and the third split may be here, and the fourth split may be here. So in this way, we can classify observations into 5 groups, which minimizes the sum of squared errors. So in this case, response variable is here. So most observations are around here, sometimes above, sometimes below, but observations are like this. The next question is how to determine the size of tree. So the number of splits t in a regression tree is determined to balance the size of tree and the total error size. If t is large, more complicated tree is made. And while bias is smaller, variance is larger. So this is the same trade-off as other methods such as multiple linear regression. So we have to balance the size of error, sum of squared errors, and the size of tree. Smaller error is better, and smaller model, simpler model is better. So here, alpha is hyperparameter. So if we choose large alpha, that means we have larger penalty on size of t. So we make smaller tree. If smaller alpha, the size of tree gets larger. Typically, alpha should be determined by cross-validation. This is a hyperparameter. Trees work in the same way for classification. Okay, the last question is, which is better, linear models or tree-based methods? It depends on the case. That is the answer. Okay, so see this example. So green area and yellow area represents the true class for this classification problem. So green and yellow represent truth. You can perceive as green area probability of y is equal to 1 is higher than 0.5, and yellow area probability of y is equal to 1 is less than 0.5. So first think about this case. And we have two cases. We fit usual logistic regression and tree-based method. So for the upper panes, actually, logistic regression works better because logistic regression has linear boundary. So if the truth is here, we can exactly estimate that boundary. If we use tree-based method to identify this true boundary, at first probably we have to set this threshold, then this threshold, this threshold, this threshold, and this threshold to conclude this is yellow, and this is green, and this is yellow. So this is much less efficient compared to logistic regression in this case. How about lower panes? In the same way, we fit logistic model and tree. In this case, actually, tree-based method is much better. If we do logistic regression, estimated curve is here, but this is poor fit because this side is estimated as green and this side is estimated as yellow, but actually we have large error here, here, and here. But if we use tree-based method, this is better in this case. Only with two splits, we can perfectly classify green area and yellow area. So linear models and tree-based methods have different strengths. So in some cases, logistic regression works better, and some others, tree-based methods are better. But in general, tree-based methods is more flexible and good for very complicated truths. Lastly, we have some more advanced methods to improve trees. So it is known that tree-based methods have higher variance. So that means the result is not stable. So this is because the split is largely determined by chance. You can think about typical example such as binary classification problem like this. In this case, probably the best split is at this point. But if we have just two more observations here, best split becomes here. So you can imagine that tree-based method is pretty unstable. So we need some methods to stabilize the results. So one method is bugging. So that is randomize the training set to make tree, and that we repeat this procedure and take the average. So in this case, some split is here, some split is here, and if we average out, we have the better criterion to represent the model. And another method is random forest. So this is similar to bugging, but each randomized sample involves fewer predictors. For example, if we have predictors x1 to x10, in the first trial for randomized training set, we only use x1 and x5. In second training set, we only use x2 and x6. Third one, maybe x3 and x10. So in this way, we can increase the randomization, and finally, if we take the average, we can expect better results. The last method is boosting. So this means that we gradually determine the tree. So at first, that we determine the first tree, then we expect that that tree determines maybe 1/100th of the truth. Then we make the residual. We take the residuals, and we can fit the tree-based method again, and we repeat that 100 times. Then we can gradually approach to the truth. So this is boosting. So we will discuss these methods later in detail, but this chapter we stop here. Okay, so now we finished the digest of chapter 8, so you can go on to the canvas and you can solve question 324-2. Okay.